In this section, we'll study the fundamental theorem for line integrals as a generalization of fundamental theorem of calculus. Let's see the recall. Part 2 of fundamental theorem of calculus is expressed as in this equation. Integral from a to b f prime of x dx is f of b minus f of a. And for function defined on interval from a to b, for f, and this one is a value at the end point, and this is a value of f at the beginning point. The difference is the integral. You learned this one earlier in calculus 2. We have a theorem here. Suppose that f is continuous and is a conjugative vector field. That means there is a potential f such that the vector field is the gradient of the potential. Then the line integral over c of the vector field can be written in this way. The vector field itself is the same as the gradient of f, and this integral can be evaluated through the potential. Once the curve is parameterized, then this is the terminal point, that is the beginning point. So that is exactly same form as the fundamental theorem of calculus. We can prove it quite easily using the chain rule and the fundamental theorem of calculus part 2. Okay, the line integral of the vector field can be written in this way when the curve is parameterized and t is from a to b. Now, this quantity can be written in this way. That is the time derivative, t derivative of this composite function. You can easily check this. Now, by using the part 2 of fundamental theorem of calculus, you can reach at this final result. Okay. The theorem is the fundamental theorem for line integrals, and here f is called a potential function of f, or simply potential. Okay, let's try to solve a couple of problems. Vector field is given in this way. Now find a function f such that gradient of f is the vector field capital F. So that means the given vector field is a conjugative vector field. Let's try to find potential f. Part A. Now if we start from gradient of f is the vector field, then it has two components. First one is f sub x, and second one is f sub y. And then from a vector field, we have two components. The first component must be same as f sub x. So we have 3 plus 2xy squared, and f sub y must be this second component, 2x squared y minus 4. Okay, we number these two equations. Then from 1, and we try to get f by integrating it with respect to x. Then f is 3x plus x squared y squared, and we have to put here a constant must be general, and so that we should choose this one rather than a constant k. You have to choose this general constant so that x derivative will make it 0, right? Okay, now what we have to do is to decide this term, right? Okay, in order to do that, from here we differentiate it with respect to y. Then this will disappear, and that will be x squared times 2y and g prime y. This one must be same as the right side of equation 2. Okay, so by matching this right side and that one, we can get here g prime y equal -4, which means that g of y as a function of y, that must be -4y, and we have to put again a constant that must be real constant k. So we found the g of y. So we can conclude f is 3x plus x squared and y squared minus 4y plus k. Okay, that's it for part A. Now for part B of the problem, here we have now line integral, and C, the curve is parameterized with this one, and we can find easily beginning point and end point because t is moving from 0 to pi. So here R0, which is beginning point, if it is 0, then that is 1, and again 0 here. And how about R pi? T is pi, then x component of the terminal point is -1, and y component is 0, right? Okay, so the integral can be evaluated from the values of f. The terminal point f at terminal point is -1 and 0, which means x is -1, y is 0, and minus, and beginning point is 1 and 0. Already we know the potential, so that by using the potential we can get a value for this. Okay, once y is 0, then these two terms will be 0. So that from this one, x is -1, so we can get -3. Okay, minus, and f at 1, 0, 1, 0, then that is a 3. So we reach at here the final answer, -6. Okay, so that's the final answer. Okay, this problem is a revisit of the earlier problem, and the vector field is given as in this equation, and C is the parabola y equal 1 plus x squared from -1, 2 to 1, 2. We want to find the potential and evaluate the line integral. Earlier in this problem, we considered this the curve and integral and vector field, and we found that the integral is 0. Okay. Now the curve is given in this way, and then that is -1, and that is 1, and of course that is height is 2, and this is 1, and curve is given in this way. Okay, now let's try to find the potential of the vector field. Okay, exactly the same way we start with gradient of f is capital F, which means that f sub x is the first component of the vector field, that is x over square root of x squared plus y squared, and f sub y is the second component of the vector field, which is this one, y over square root of x squared plus y squared. Again, we number the equations, and from the first one, now we try to get integral with respect to x, then f is, okay, that is now x squared plus y squared and a half power. Then easily you can see that the derivative will be exactly that one, and the constant, a constant must be a function of y. Okay. Then we have to decide this one. In order to do that, we try to make y derivative. Then that one will be half and x squared plus y squared and minus half power and 2y and plus g prime y. Okay, we can rewrite this one. Then 2 and half will be cancelled, and we have y on the top, and that can be written here on the bottom, square root of x squared plus y squared and plus g prime y. Now we compare this term with the second equation. Then we can easily see that g prime y must be 0. That means g of y is now a real constant. So we may ignore when we try to evaluate the integral. So we conclude here, f is now square root of x squared plus y squared. And you may put k or ignore this portion. Okay, we found a potential, and let's try to evaluate this integral. That must be, the given integral must be here f, that is end point, okay, let's say that is e, and minus f of beginning point, right? But we already know that the end point is 1, 2, and the beginning point is minus 1, 2. Okay. Now, x is 1 or minus 1. This value is always the same because it's squared. So that f12, f minus 12 will be the same. So the subtraction must be 0. Okay. So we got the answer. Okay. Let's move on. We define the independence of a path. In this definition, we say the line integral is independent of a path if the line integral along C1 and C2 are the same when C1, C2 have the same initial and terminal points. Once beginning points and end points are the same, then independently of the path, the result is the same, only depending on beginning and terminal points. Then in this case, the integral is independent of a path. That's the definition. In general, the integral is not independent of a path. And we already considered some examples. However, once the given vector field is conservative, so that we have potential, then the integral is independent of a path. Let's see this equation. Integral along C1 of the vector field can be written in this way. Now, from the fundamental theorem of calculus, we can evaluate with this term the potential at end point, terminal point, and potential at the initial point. Now, for another curve, C2, the integral can be written in this way, and along with the gradient of potential. Now again, using the theorem, we can reach at the same quantity. So once the vector field is conservative, then the integral must be independent of a path. So we can say here, conservativeness implies independence of a path. Now we'll study some more properties of conservative vector fields. In order to do that, we need a little bit more definitions. A curve C is closed if its terminal point coincides with its initial points. Okay, let's see these curves. Now, if we consider this curve, then and choose any initial points, then now the curve is now end at the same point, so it is closed there. But for that one, and there's initial, then there will be terminal point, so that they are not the same. It's not closed there. And also for that one, here, if we start with any point, then anyway, the curve end at the same point, so it is closed there. But for that one, it's not closed there quite clearly. Now we have another definition. A simple curve is a curve that does not intersect itself. And okay, let's see for that one. This curve is not intersecting itself, so it is a simple. Again, this is a simple, but this one, the curve is intersecting here, so that is not simple. Again, we have here intersection, so it is not simple. Okay. The line integral of a vector field is independent of a path in D if and only if the line integral is 0 for every closed curve, every closed path in domain. And we consider a domain. Inside a domain, now the path curves are considered. Now the integral is independent path, and that is the same as the 0 line integral on closed path. We can consider this one quite easily and pictorially. Okay, we choose a point and another point, and a path is given. Now, if it is independent of path, then even though we choose another path, So that's a C1 and C2. Then the integral along C1 and integral along C2 must be same. And when we assume the integral is independent of a path. Now, if we consider the opposite of that one, reverse minus C2, then here, okay, then this value is exactly negation of that one, so that if we consider this closed curve, then the integral must be 0, because this value, the value along these two curves must be the same. And if we consider reverse, then the negation of the integral, so that they cancel out to become 0. And also, for every closed curve, we consider a point, initial point, and again another point. Then now exactly we consider this portion and that portion. Then again, because it is independent, if it is 0, then this one, the value must be any value here. The other side, there must be negation of this integral, which means that if we go that direction, then this integral, that integral must be the same. The proof is based on this geometric interpretation. So we can say independence of path is same as 0 line integral on closed paths. Okay. Now, to consider more properties of line integrals of conservative vector fields, we need some more definitions. This is not open, but it's open and not open. Okay. Let's consider an interval from 0 to 1. Then this interval is open interval. The reason is, if you choose any point inside the interval, then you can make a subinterval including the point, and this subinterval is inside the original interval. No matter how close the point you choose, it doesn't matter. You can find the neighborhood of the point which is inside the whole interval. The same way, now if we choose any point in the domain and region, and you can make a disk, small disk, which is wholly inside the region. So that is open. If it includes a boundary, then at the boundary, if you make a disk, then no matter how small the disk is, the part of disk must be outside the region. So it's not open. It's open, not open, not open. Okay, now we'll define connected domain. Once we are missing a line, then it's not connected. So we say this is disconnected. This one is connected. This wasn't connected through this area. Here, connectedness is defined in this way. If you choose any 2 points, then you can find a path from one to the other point, and so that the path must be in the region. For this one, if we choose these 2 points, then we cannot connect from here to there, and crossing this line, that must be outside of the region. so that we cannot connect. But for this one, we can connect for any 2 points. Over there, again, we can connect these 2 points, and passing through that one, we can connect these 2 points. So these are connected. Now we can easily see this one is disconnected. Of course, this one is again disconnected, but this one is connected. These are pictorial definitions. We'll go to here mathematical definitions. A set D is open if every point P in D has a disk with a center P that is contained wholly and solely in D. There is a mathematical description of this pictorial explanation. So that the open region cannot contain any boundary points. Once you choose the boundary point, then any disk should have a path outside the region. A set D is connected if for every 2 points P and Q in D, there exists a path which connects P to Q. Okay. Now we have a theorem. Suppose that the line integral of a vector field is independent of a path within an open connected region, then, okay, now is independent path, then F is conservative vector field. So the theorem says independent of path implies conservativeness when it is defined on open connected region. But earlier we made a conclusion that conservativeness implies independent of path. So eventually, once we consider open connected region, then they are the same. Here we have the sketch of proof, and if you are interested in mathematics, then you may try to read. Okay. So as a corollary, we can get here the claim. In an open connected region, F is conservative if and only if its line integral is independent of path. In most cases, we'll deal with open connected region, so that we can say conservativeness is the same as independent of a path. Okay. Okay, we'll continue in the second part. Thank you.